All right, 9-8. Yes, we're out of order. Don't ask about 9-7. It's coming soon enough. You'll be excited about it. Number one, we're going to actually run through and we're going to prove a couple of theorems that make logs really, really cool. Frankly, if the only thing that logs did for you is give you a notation by which you could undo a power, we wouldn't teach them to high school students. What they do that's really, really cool is they have a bunch of properties that involve exponents that you normally don't have down here in the normal land. So it allows us to do a whole bunch of things we cannot do in normal land. And so we're going to try this thing out. First thing I'm going to do is I'm going to look at this. I'm going to say, look, I'm supposed to give you a proof here. I'm going to go no duh again. Right? So this gives me A equals B. Is that fair? And that's what it's going to be. Okay, so moving on to the next one. The next one's proof is going to be a little trickier. So I'm going to go ahead and give myself a whole page. And here we go. It's going to be log base x of A plus log base x of B is equal to. Now, in order to do that, first thing I'm going to do is I'm just going to randomly, I'm going to set that y, log base x of A is equal to y. I'm going to say that log base x of B is equal to z. Let's call it z. Okay, so far so good. And then what I'm going to do is I'm going to go ahead and go, all right, well then A equals x to the y, right, swinging it around like a orangutan, and B is equal to x to the z. So far so good. And then I'm going to do something really fun. I'm going to say that A times B is equal to x to the y times x to the z. Now there's nothing wrong with that. What I'm doing is just taking what I have here, multiply them together, and I'm multiplying those sides together, right? Totally allowed. Now I'm going to recognize, wait a second. Wait just a minute. I know how to do this. I got AB equals x to the y plus z, right? Because the base is the same. I can add the exponents. Gets even better. Let me log it. Swing this back over. I get log base x of A times B is equal to y plus z. And remember, y plus z is this right over here, right? So I'm going to replace those back in. I get log base x of A times B is equal to log base x A plus log base x of B. So addition outside is multiplication inside. Now that makes some sense because if you think about it, log is power. This is really a power, right? To what power do you need to raise? To what power? If I'm adding exponents, that's the same as multiplying their bases. Right? Right. So then we try the same thing. We go, wait a second. I'm going to try log base x of A minus log base x of B. I'm going to haul through this because you've seen it all before. And you can guess what the answer is going to be, but we'll do it anyways. And look at this. I'm ripping right on through, not even paying attention. And now this time, instead of doing randomly A times B, I'm going to do A divided by B. Ooh, look at that. I had x to the y over x to the z, which is x to the y minus z. Realizing that I had an x as a base, I'm going to swing it over. I go log base x of A over B is equal to y minus z. Y and z, we remember, are those logs. They're this thing here and this thing here, right? So then it's going to be log base x of A minus log base x of B. And again, these are exponents. If I subtract them, what I'm really doing is division. And so it's totally allowed. Totally allowed. And that's the other property that's really, really fascinating. And those two properties by themselves are worth money, but there's a better one. Here comes the better one. So everybody see this? Give you a moment, write those down. Make sure you write down the ones that are circled. I'm not going to actually prove these, but it's important you see the proof at least once so you don't go, well, I have no idea where this came from. It's just magic stuff. All right, moving forward, let's try the last one. The last one's even more fun. It's log base x of A to the B. Now, that's going to be equal to log base x of A times A times A times A times A, B times, right? Whatever B is. Agreed? B times. So that's the same at, well, see, multiplication inside is addition outside. That's what we just proved. So this becomes log base x of A plus log base x of B plus log base x of, sorry, it should be A, log base x of A. How many times are we going to do that? I'm going to do that B times, right? Which means this is equal to B log base x of A. This one here is incredibly powerful. Whoops, I should make my B's the same. I apologize. My B's should all be the same. I don't know why I changed B's, but I did. Okay. So, what does this mean? You can take this exponent if it's inside the log and throw it out in front. Doesn't matter what log it is either. I didn't have any constraints on my base. My base was whatever my base would be. Doesn't matter. So I can always take an exponent if it's logged and throw it out in front. Oh yeah. Now normally I'd flip the worksheet over, but we're not going to do that. Instead, we're going to go ahead and start looking at assignment 9-7. And on 9-7, what I want you to do is I want you to try actually, what I want you to do first is I want you to get 9-7. So we're going to pass out 9-7, and then once everybody's got 9-7, we'll start this again. Now there's some additional notation stuff we have to take care of. For example, what is meant by a log without a base? And so we're on top of 9-7 now. I know I guess you'd be at 9-8. Now you're back on 9-7. Let's take a look, see at 9-7. It says, what is meant by a log without a base? Well, the very first logs that were ever done were all the same base. And so we never actually understood that this might be handy for different bases. The first log that was dealt with was log base 10. And so if you have to write log base 10 enough times, eventually all you write down is log. And so when I don't have a base written down, it is implied that that is log base 10. Okay, those are the same thing. What is meant by ln? Well, ln's got a special place in our heart because ln is actually log base e, right? The natural number comes back into play. You have that button on your calculator. These two right here are the most significant, the ones you're going to use the most by far. In addition to that, you can do any other log, we'll explain that later, if you know how to do these two. You know these two, you can do all the rest of them. And so there is that. Okay, so now let's take a look-see. Go ahead and try to take a stab at 1 through 4. We're going to go ahead and play with those and give you a moment to do that. So I'm going to pause it. Pause now, and we'll do the problems when you guys got a chance to do it. All right, so I hope you had a chance to do those. Now we're going to play, and the playing is going to cause you great distress, and then eventually great joy because life is good. And good life is good anyways. So I've got 2 log of 4 minus log of 2, and then I've got -3 log of 1/3. Okay, so now I'm going to play the game of how does this all go together. Take a look at this. First one, I got log base 2 to the 1/2 power. Remember, roots are the root of all evil. You do not want a root ever. Ever. Always going to be a problem. Okay? So then you would move forward and you would look at this and go, well, addition outside is multiplication inside. So I'm going to go log of 2 to the 1/2 power times 8 to the 1/2 power inside my parentheses. Yeah. And then, since the powers are the same, I can multiply the bases because I can rewrite it as log of 2 times 8 to the 1/2 power. Hopefully you remember that. This becomes log of 16 to the 1/2 power. Oh, this is so painful. And then I got log of 4. Yes, log of 4. Got that one? I'm just going to show you how to play with all these. Log of 4 minus log of 10. Subtraction outside is division inside. So 4 over 10. So that'd be log of 2/5. And I think I'm done with that one. Hopefully that's a match. Yes, that's a match. Next one would be 2 log of 4 minus log of 2. I might throw that 2 back in. Oh yeah, remember power of multiplication outside can be thrown in or taken back out. We might want to do that later anyway. So log of 4 to the second power is 16 minus log of 2. Subtraction outside is division inside. So this becomes log of 16 divided by 2, which is log of 8. Oh, this is fun. And let's do the last one, which you now know it needs to be log of 27, hopefully. It doesn't make sense. Whatever. Okay, log of 1/3. I throw this back in. This becomes log of 1/3 to the negative third power. Oh, wait, negative third power means I get to flip it. Log of 3 to the negative 3. Oh, not to negative 3 because I got rid of the negative. My bad. Becomes 3. This becomes log of 27, and I'm done. Fair enough? All right. The mental health workers are going to come any minute now and come see Mr. Resney talking to himself in a room. All right, things I do for you guys. They good? Okay, I'm going to leave these examples up here. Go ahead and try 11 through 16. What is meant by expand is they want you to write it in as ugly a fraction as you can. So for example, log base 3 of 3x. Well, that would be log base 3. Multiplication inside would be addition outside, right? Plus log base 3 of x. I have officially expanded it. Yes, that's expanding it right there. Got it? Everybody try 11 through 19. I mean, 19 looks like this. 6xy squared over the square root of z. Yes, you'll enjoy that one. Okay? And then condensing. How do you condense? Let's look at number 20. Give me a moment to find number 20. Sorry, I keep saying you could do the problem. Give yourself a moment. Try number 20. Here we go. Number 20. Log base 3 of 4 plus log base 3 of 2 plus log base 3 of 2. So, since we just said expanding means write it as ugly as you can, condensing means to collapse it down to where I can do the problem one step. Addition outside is multiplication inside. This is log base 3 of 4 times 2 times 2, which is log base 3 of 16, and I've already done. That's condensing. Got it? All right, have fun.